Okay, so hello Simon. Today it's a privilege to introduce Dr. Simon Thorpe, a pioneering neuroscientist and I would say AI innovator. Dr. Thorpe is an Emeritus CNRS Research Director at the Brain and Cognition Research Center, or we call it CerCo, in Toulouse, France. He earned his doctorate in experimental psychology from University of Oxford under the mentorship of Professor Edmund Rose, and has since forged an impressive career exploring neural mechanisms and computational neuroscience. In fact, in 1993, he co-founded CerCo, am I right?
Yep.
And has significantly advanced the understanding of visual processing and rapid categorization in the brain. Simon is known for his innovative approach to neural coding, emphasizing ultra-fast visual recognition and neural efficiency, which inspired the creation of a SparkNet technology in 1999. A bio-inspired tech company that he established to develop
used to be just about 100 meters from here at one point.
Hardware and software for image processing, but later acquired by Bradley in 2016. In today's talk, what can AI learn from the brain, past, present, and future? He will explore how brain-inspired models could redefine AI, emphasizing the efficiency of the Spark-based coding and brain's rapid learning capacity. Thank you very much. Thank you, Simon.
Thanks, Milad. So I've known Milad for a long time. I was in his thesis committee quite some time ago. And then he also spent nearly 3 years at the CerCo as a postdoc before you were lucky enough to recruit him here, because I thought he was going to be a CNRS researcher, but anyway, yeah, so I actually retired last year, but I'm still trying to keep some projects going. What I want to talk about today, I'm going to give a sort of personal history of the links between artificial intelligence and neuroscience. Ways in which the brain can be a source of inspiration. They go back to the ideas of artificial neurons, but also something that I've been working a lot on, which is sort of feed-forward architectures for recognition and categorization. I'll also talk about spike-based coding, which is one of my favorite things, and also unsupervised learning. So a lot of the learning models used in AI are very much supervised learning, and I think the brain's speciality is that we don't need to have labeled data, things just get learnt anyway. And this allows us to sort of move towards what I would like to think of as brain-inspired AI. And my latest stuff I've been working on for a few years now is the idea of sort of terabrain systems, neurons, simulations with literally, potentially billions of neurons, or even hundreds of billions of neurons running on very low power hardware. And that includes running things on Macs. And with Milad, you may have seen him working away with an M3 Mac that I've loaned him. And one of the things that we think we can do is to simulate very efficiently very large networks. And I think this is important for AI, because you see companies spending fortunes, hundreds of billions of dollars buying hardware to produce huge AI centers. And I think all of this doesn't make any sense when we know that the brain uses 20 watts. Right, so here's my little quick history of AI and its links with the brain. So back in 1943, Warren McCulloch and Walter Pitts came up with the threshold logic units, which is a very simple idea of neurons doing Boolean logic, if you like. Obviously, there are people like Turing, Alan Turing, thinking about computers and thought and so on. But I think it was in the late 50s, early 60s that Frank Rosenblatt really sort of took this quite a long way with the idea of a perceptron, which is just like a logic unit, but where you can do sensory processing using sort of weighted sums of inputs and some output function. And during the 60s, this was really very, very popular until 1969 when a book by Marvin Minsky and Seymour Papert came out called Perceptrons, which basically blew the whole field apart because they said there are certain type problems that you'll never be able to solve with a perceptron, and therefore, you know, we have to do something else. And so the neuro-inspired AI thing just went completely dead, literally. And there was what you can call a sort of the first neuro AI winter. Now, I started my thesis in like 77, and I was recording neurons in the monkey brain that were doing things like responding selectively to foods, like bananas, whether the monkey saw the banana or tasted the banana. It was a sort of multimodal cell that was coding banana as a concept. And I sort of thought, there must be learning going on. You know, what sort of model can I imagine to explain how these multimodal units come around? So I was looking around for models that were relevant to understanding this. And I can tell you there was essentially nothing. Nobody was doing that sort of modeling at all, except one guy, Fukushima, proposed a thing called the neocognitron, which was one of the very first sort of convolutional neural networks. But then things started really moving, and John Hopfield in 1982 came up with the Hopfield net, for which he just got a Nobel Prize. You may remember about that 2 weeks ago. Around the same time, Dave Rummelhart and Jay McClelland came up with what they call the interactive activation model of word recognition, where you have sort of units and they have connections and so on. This was one of the very first, what we call a connectionist model. And then 1986, we had Geoff Hinton, Yann LeCun, both very well known now, independently coming up with the idea of backpropagation learning algorithms. And then there were these two books that came out by the PDP group, Parallel Distributed Processing Group, which, you know, in my time, these were just like the Bible. Every lab had these books. So there was sort of, and of course, there was this paper in 1986 on learning representations by backpropagating errors, which has become extremely important, probably even now for you guys. At the same time, another big name was Terry Sejnowski. He'd go around talks showing a little neural network model that would learn to read text and generate speech. It was a text-to-speech conversion thing. It was all done with actually a remarkably small number of units. There were only sort of like a hidden layer had a few hundred units, and it would learn to generate text from speech. All very impressive. I was there. I thought, oh, this is fantastic. We're going to solve how the brain works. It was going really, really, very well. But then, for me, something else happened again. It was in the early sort of 90s. There was things like support vector machines and other sort of machine learning algorithms. And I used to go to conferences like NIPS, Neural Information Processing Systems, and I tried to find some of these engineers who I could talk to about the brain, and basically they weren't interested. It was all sort of algorithmic approaches, very mathematical. Nobody was really interested in the brain at all. It was all pure sort of engineering and maths. And so, at least as far as I was concerned, there was just like another second neuro AI winter, because, you know, basically these communities were not talking to each other. And then something very significant happened in 2008-9. Fei-Fei Li came up with ImageNet. This is a challenge where you're given. She labeled millions of photographs in different categories and proposed a benchmarking test for image categorization, where you basically you train your system and then you get tested. Here are lots of images that the system has not seen, and it has to say which of 1,000 different categories does the image belong to. At the time, people thought she was completely mad because, you know, this is an impossible task. You know, nobody knows how to do it. But within 3 years, Geoff Hinton, again, Nobel Prize winner also, and his two students, Alex Krzyzewski and Ilya Sutskever, came up with AlexNet, which is this is in 2012, ImageNet classification with deep convolutional neural networks. cited more than 163,000 times. This is absolutely phenomenal. And it was the dumbest system you could come up with. It had 7 layers. It was a pure convolutional feed-forward neural network trained with, we know the number of neurons, number of parameters, number of synapses. These are the receptive fields of the neurons in the first layer. There are 96 of them, and they actually look at quite a bit like neurons in the visual system. But by the end of this, you've got 1,000 neurons, which are neurons that classify what category an image belongs to. And with that, if you look at this graph here of ImageNet performance in the early days, in the first few years, this is the blue dots are classic computer vision. And then this point here, this is AlexNet, and it just blew the field apart, halving the error rate. At that time, the next year, 2013, there was this guy at Stanford who trained himself to do ImageNet classification, and he said, I can get, I got 94% correct. We're better than the machines. But the year later, it was all over in a sense. I mean, the machines were doing superhuman performance. This is a really difficult task. You have to know 57 breeds of dogs and so on. It's really quite a challenge. But it didn't stop there, of course. 2017, Google Research came up with a transformer model, and the rest is history. I mean, we've got all the sort of people like OpenAI with GPT-3 and 4 now, and Meta Llama and Google Gemini, Anthropic Claude, Mistral AI in France, and so on, producing these amazing AI systems. And we're now talking very seriously about artificial general intelligence and even super intelligence, depending on, Elon Musk, a few days ago, he was saying, we're going to have systems more intelligent than the entire population of the planet within 5 years, that sort of thing. Right. So now, what have I got to do with this? It happens that in 1989, I wrote a sort of review paper. There was a conference on connectionist modeling, this PDP thing. And I was, as a biologist, I've been recording neurons in the visual system, and I knew that they responded to things like faces in about 100 milliseconds. And I said, oh, well, these neurons are 10 layers away from the retina. You have to go through 10 layers. You get 10 milliseconds per layer. It has to be feed forward, I said, because you don't have any time to loop back on anything. And this was sort of, I did some experiments to actually test this a bit more. And we did this experiment, my biggest hit, most cited paper I've got, which is on flashing images for 20 milliseconds that you've never seen before. And you have to say whether there's an animal in the picture. And people can do this incredibly well. It requires no effort at all. Basically, it pops into your head, this is an animal. Even if you don't know what you're looking for. The position of the animal, the side of the animal, the background, doesn't make any difference. The system works perfectly. And, this is one reason why we developed models of visual processing in which basically the image comes in and then it sort of runs through all these different visual areas. I won't go into the details, but this is the layer at which the neurons respond selectively to, for instance, faces. Now, we did lots of research on this, and Rufen van Rooyen, who was my student, went off to do a postdoc at Caltech with Christoph Koch, Pietro Perona, and the student there was a certain Fei-Fei Li. And they had this paper, for instance, in 2002 on rapid natural scene categorization in the near absence of attention. We were doing similar sorts of things on this, basically showing that the brain you don't have to think about it, it just happens automatically. And that really got her thinking. And it was the reason why, when she went to Princeton, she decided to come up with a task which really looked at this, not just for animals versus non-animals, but for all categories. And that was a major step forward. So, I think there's a sort of case to be made that Fei-Fei Li's decision to come up with ImageNet as a really hard problem came from the fact that she'd been working with the task that we invented here in Toulouse in 1996, he says modestly. It certainly pushed a lot of people say, hang on, how is it possible that you can recognize these objects in a system where you have no time to do anything, basically, apart from just a feed forward pass? In other words, exactly the sort of architecture that Jeff Hinton and his two students came up with 3 or 4 years later, a pure feed forward model. So, you could say, oh, well, okay, so the brain did actually drive that move towards using natural images, categorization, and so on. Is that all that there is to learn from the brain? Will AI continue to develop as it is at the moment, with basically everybody ignoring, this has anything to do with the brain? Well, I would say absolutely not. And I'm going to try and convince you that there's still a lot of stuff to get out. Classical neural networks, which are the things that you find in all these deep learning systems, basically use neurons which you got a neuron here which receives, in this case, 16 inputs, and these inputs have different values and it has weights. And then basically what you do is you code the activation of the inputs with floating point numbers, you code the weights with the floating point numbers, you multiply the things together, and then you add them all up and you get some number, and then you put that through some function, which can be a sigmoidal function or a rectifying linear unit, and you get another floating point number as a result. And this is what all your GPUs are doing, essentially this. It's just massive amounts of, that's with 16 inputs on one neuron, and it's 16 multiply and adds plus the transfer function. In all of these things, any of the large language models with billions of parameters, every time you ask it anything, it has to do a zillion calculations, which are very expensive to do. And this raises the energy problem, because if you thought this was a sensible model of how the brain works, and you wanted to simulate the human brain, which has 86 billion neurons, each one of which has several thousand inputs, let's say 7,000 on average, and you want to recalculate every neuron state every millisecond because you want it to be able to react rapidly and so on. Well, you just do a quick calculation, 86 billion times 7,000 down to 1,000. You need 600 petaflops to do that if you're going to do the brain this way. Well, look, if you look at the supercomputer top 500 list, there are indeed 3 computers that could actually do it. They're all in the States, and they all use over 20 megawatts of power. Now, Europe is fighting back. We're going to have the Jupiter exascale computer in Germany at the end of this year. Here it is. 2,300 square meters of computers. It uses only 18.4 megawatts of power, so it's less than 20 megawatts. But this is insane, because you're just doing this to simulate a brain which uses 20 watts. It's 1 million times more energy consuming than the human brain. So what's missing? What's the secret? How does the brain get away with it? Well, if you're Jeff Hinton, and he's a very Nobel Prize winner after all, he's got over 850,000 citations. This is absolutely insane. Now, if you hear him talk recently, last year even, he thinks that the brain uses very low power analog computing. So effectively, you can do computation without using digital, no floating point, anything. You take the inputs of voltages, the synapses are resistances, the amount of current that goes through is effectively a multiplication. And he has suggested that these sort of memristor architectures, which are actually very popular, lots of you working on this sort of thing, where you have a sort of crossbar array and you have variable weight resistances and so on. This could be the explanation. And I don't want to say that this is wrong. It might be relevant. But I would like to suggest there's another hypothesis, which I think actually will give you a lot of advantage, and that's to use spikes. Now, the fact is that neurons never send continuous values, at least not over any long distances. They send action potential spikes. That's a nice recording of a neuron in the cerebellum sending these pulses. And the problem is that everybody knows that neurons send spikes, But in classic AI, where you're using floating point numbers to code the activations of the weight, we know that neurons use spikes. And for some people, is that a problem? No, because we're supposed to believe that the floating point numbers are effectively correspond to the firing rate of the neurons. And so we can forget about the fact that the brain uses spikes. But I think that's totally wrong, because of that energy problem. It's just extremely expensive. Even if you can do it, you can definitely do it. It's just not a very sensible thing to do. And rate-based coding is actually, if you just measure the firing rate of neurons, it's extremely inefficient as a way of doing things. There was a fascinating debate last year on the future of high-performance computing. Are neuromorphic systems the answer? And there were two pairs of people, Bowen from Stanford, Etienne Cummings from Johns Hopkins, versus Yann LeCun, our favorite French scientist, and Bill Daly, who's the chief scientist at NVIDIA. These guys were pro-spikes and these guys were anti-spikes. And Bill Daly, you can watch this, it's actually quite extraordinary, because he says at one point, well, if you wanted to send information, NVIDIA chips, we use, various things like, 8-bit integer or floating point or whatever. We would never use spikes, because he says, in order to send an 8-bit number with spikes, he says you'd need to send up to 255 spikes if you count them. And that just proves that these guys have not a clue, because that is not a sensible way of sending information. So the spiking view, which dominates, actually, amazingly, it's not just people like Bill Daly that believe this. It's actually quite a lot of neurophysiologists who believe that it's firing rate, which is the code. So if you want to believe that it's the rate of firing that counts, there are several ways that you could use the spikes to. Here we've got 16 neurons with different rates, and they're firing at different numbers of spikes during the period. Or you could actually, if you wanted to be a little bit more efficient, you just need 2 spikes and you measure the interval between the 2 spikes. That's an instantaneous rate code. Except it's actually very difficult to decode that accurately. The worst thing, which actually a lot of people amazingly believe, is that it's Poisson rate coding, where that neuron that's got calculated its activation level has to throw a dice, every millisecond to decide whether to generate a spike or not, and you get a Poisson rate code, and it's absolutely catastrophic, as I showed with my student at the time, Jacques Gautret, in 1998. It is absolutely useless. It never do that. They're all really bad, especially because there's a perfectly good alternative. Rather than using rate at all, you just use 1 spike per neuron, and you code the information in the order in which they fire. And this actually works for a very simple reason. If you can think of a sensory receptor like a neuron in the retina that's coding in light. If you give it a weak stimulus, it sort of charges, it's like a capacitor with a threshold. It charges up, and when it gets to the threshold, it fires a spike. If you have a stronger stimulus, it fires earlier. And with a really strong stimulus, you can get the latency really short. And this is a well-known phenomena in neurons. Everybody knows this. And you get these sort of intensity latency functions. As you increase the intensity, the latency of the spike drops. If you think this is what's happening, it means that you're thinking of the sensory neuron as an intensity to delay converter, rather than the conventional view, intensity to rate converter. Now, obviously, these neurons, if they kept firing, that you would get a rate, but you don't need to measure the rate, because you already knew the information at the beginning, as proved in the very, very first paper ever published on the neurophysiology of the visual system by Lord Edgar Adrian in 1927. He got the Nobel Prize for this. And this paper, Action of Light on the Eye, he was recording from fibers in the EEL optic nerve, and he just illuminated the retina with two intensities of light. And he had this actually quite an ingenious system for measuring the sort of a graph of the firing rate. The stimulus comes on for 3 seconds, high intensity or low intensity. You can see with the high intensity stimulus that the instantaneous rate at the beginning is definitely higher for the high intensity stimulus. You can see that the maintained firing rate at the end is actually even more bigger. There's a big difference here between these two things. But look, if you look at the very beginning of the response, the neuron with the low intensity stimulus takes 200 milliseconds to fire a spike, whereas here it's like 100 milliseconds. So you already knew that it was a high intensity stimulus if you looked at the latency of the first spike. And that fact was ignored by neurophysiologists for several decades. And it was only in the sort of 2000s that people started to think, oh, well, maybe we can get right. So this I only discovered this actually sometime after I'd been thinking about this, because actually I mentioned this in the same paper where I talked about the feed forward thing. I'd sort of made the suggestion that the arrival times of spikes could be a code, and I put that in another very short 4-page paper at a conference in 1990, spike arrival times, not realizing that actually this had been shown in 1927. Well, he didn't actually put it like that. And then with my students, Ruben van Rempelen, Jacques Gautret, Arnaud Delorme, this is in 1998, we had a system that would recognize, that would detect faces with just a wave of spikes going through the visual system. We have a sort of retina with on and off cells and oriented filters. And here we actually had a layer with eye and mouse detectors, and then a face detector that fired if you have a left eye, a right eye, and a mouth in the right position, etc. That was in 1998. The year after, we said, oh, this could be useful, and we set up spikelet technology with my two students in 1999, and we had offices very close to here. Why have you never heard of it? Well, actually, it's a very long story. Basically, the owners never wanted us to sell anything except anything. Well, and in the end, we were struggling, and we got bought out by BrainChip, who went on to build. They market a chip called Akida, which is a spiking neural chip for processing. It's an edge computing device, and you can wire in various types of detectors and so on. But early on in the days at SpikeNet Technology, we realized that actually when you're using a wave of spikes, here we've got 16 neurons firing spikes in a particular order. So we're coding the intensity. The gray level here is converted into an intensity where the most active neurons fire first. You can get a lot of information. You could use the ordering, and in fact, we came up in 1998 with a decoding scheme where you can decode the order. Trouble is, even with 16 inputs, the number of possible orders is like 21 trillion. 16 inputs, because how many different ways of ordering 16 letters is astronomical. It's way over the top. But we discovered that if you do a simple trick of just letting the first n spikes go through, and actually with binary synapses, this works extremely well. So here's the idea. You take your spikes, and you have a sort of relay cells, which have a little inhibitory circuit, a winner-take-all inhibitory circuit, which if they count the number of neurons that have fired spikes, and they block propagation for any neurons which didn't get in the first K, in this case 4. So in this case, that firing pattern here gets converted into just 4 spikes, because by the time the 4th spike is fired, the inhibition kicks in and nobody else gets through. You can actually do it even cheaper by putting not even having relay cells. You can have an inhibitory circuit in the input array, and that way the other 12 spikes don't even get generated at all. You just pick off the top 4. So that's even more power efficient. Not even one spike per neuron, it's 4 spikes per 16 neurons, or whatever you decide to use. Oh, sorry, yes. By the way, yeah, do stop me and ask questions. Yes.
So, basically, you said that because ordering the 16 neurons is like very high in computation, you choose, for example, 4 of them.
Yep.
But how do you choose them? I mean, there is a
Oh, it's
mechanism.
no, basically the trick is to learn the 4 that fire first, and that's precisely what we're doing here. So here we've got the same thing. We've got 4 neurons here. Let's assume that I've just randomly assigned binary weights here. It just turns out that this particular neuron, you get the 4 spikes hit the 4 weights, which actually work. You get a count of 4 out of 4, and you say yes. The other ones, you get 1 or even 0 spikes, so they don't work. No variable weight. It's all binary. Okay. And each neuron will fire to a specific pattern. So as we change the which neurons are firing and picking off the first 4, this is actually already extremely selective, because if you know your maths, if you want to calculate how many different ways of choosing 4 from 16 there are, I think it's something like 7,000. That's just with 16 inputs. If you choose 4 from 100, it's 100 times 99 times 98 times 97. It's enormous. So just as an illustration, you can do face detection with 4 spikes. Here I've got a 3x3 retina, and there are only 2 types of orientation detector, horizontal and vertical. And we just pick off the first 4 neurons to fire, wherever they are. In this particular case, the 4 that fire are these ones, and this is actually a face detector. And I've done it with 18 inputs, binary inputs, and this little circuit for picking off the first 4, and binary synapses, and it does the job. I mean, it looks like a face. Very difficult not to see a face when you have 3 horizontal lines and a vertical one in the right position. So that's actually what we invented in between 2000 and 2002. It's a one-shot learning rule where it's a bit more than a 3x3 patch. We actually have a sort of 30x30 patch, and it's not just 2 orientation, there are 8. But apart from that, it's the same idea. And so this patch has the first neurons to fire at each point. There are 8 orientations, and you pick off the first n. In this case, I put them all in, but actually you don't need all 256 units. So it's the same idea here, but the great thing is it actually works extremely well. So if you create a model, you pick a patch of any image and you learn it. What you do is you create a sort of neuron with binary weights from the orientations that fire first, and then you actually, it's a weight sharing thing. So you copy that neuron everywhere. And so the red dots here correspond to the neurons that have gone over threshold. And as you can see, this is the original image, and you get a nice big patch of neurons because it's a bit of position invariance. But look, you can have the luminance down so low that you basically can't see anything. The contrast can be very low. You can shift all the luminances up and down every way you want. You can blur it. You can add noise. It still works. And the reason is the ordering of the firing is incredibly robust. It doesn't matter. You can lower the contrast. It's the same neurons are going to fire in the same order, whether your image is very low contrast or not. What happens when you lower the contrast is the system takes longer to get the spikes, but that's all. It's still, and this is one of the uncanny things about human vision. You know, when it's foggy, there's hardly anything to see, and yet you can recognize a face or whatever.
Sorry,
yeah.
All of these changes are the variation of contrast, no? But if you rotate or if you like.
Yep. Okay. Right. Good question. Well, what happens when you rotate it? This is one model, and we've rotated by plus or minus 10 degrees, and it still works. Same model, I changed the size by plus or minus 20% roughly, still works. I take the image and I warp it as if, you've got this image and you're doing this. It still works. And it's incredibly selective, incredibly selective. That's exactly what MELAD has been doing for the last few months, because we patented a thing for image indexing, where you take any image and you just create a spike net model for it. And it will be an extremely good test to see whether the image you're showing is actually close to the one that you showed. Now, nobody's heard of this. And yet it really did work. And we never patented it, actually, because in 2002, patenting this sort of thing is just an algorithm. So pretty tricky. We did talk about that. Nevertheless, I did have a couple of papers where you can actually see what we were able to do over 20 years ago. This is the SpikeNet Vision Model Builder. We've taken this image here and we've learnt the eye here, and you can see with one model it's found two of them. Okay, you can see I1 and I2, and it took 5.7 milliseconds, of which 4.3 milliseconds was processing, pre-processing time actually. And so the cost per every model you added was about 1.4 milliseconds extra. Here's another example. Here I just this is 2002. I just made a sort of montage by taking little bits of images, Batman, Bambi, Fleetwood Mac Rumors, The Shining, Michael, just absolutely random images, and I learnt each of these. So there's a little model for each of these, and all these circles mean that there was a neuron firing at the center of that thing, telling you what the thing was. And that's 51 targets being looked for everywhere in an image which was 298 by 200 pixels. And the processing time in 2002 was 241 milliseconds. I can guarantee if you did that on today's hardware, it would be, I don't know, microseconds. I mean, it's so cheap to do, right? Now, so SpikeNet versus the brain, well, it's a really, really cheap system, because you take an image, you just run a bunch of convolutions on, and then you've got the recognition layer, which is, for every thing you want to recognize, you have a layer of neurons. And this doesn't look like the primate visual system, which has actually 7 layers and so on. And actually, AlexNet looks a lot like the real visual system. And when Jeff Hinton and co came out with their thing in 2012, I wrote to Alex Krzyzewski and said, "Why did you choose 7 layers? I mean, do you know that's the same as the primate visual system?" He said, "Oh, we just tried it and it worked." That was his response. Now there is a big difference though. The AlexNet and the human visual system won't necessarily be able to tell you on the first pass where the objects are. It'll be able to say, what type of dog it is, but it won't be able to tell you the dog is here or count how many dogs there are. Whereas SpikeNet would. It would, if you have a large image with 100 faces in it, it will tell you where every one of them is, and it does it extremely efficiently. Now, does the brain actually do that sort of thing? And the answer is no, with one exception, and that's faces. We developed a task called we call it the face zapping task, where subjects are sat in front of a screen, they've got an eye tracker, you get an image, and there's somewhere in the image there's a face, and you have to look at the face. And then as soon as the eye tracker says you found the face, you replace the image with another image that you've never seen before with another face that's been pasted in, and then you just do that 500 times. And this is what it looks like. Oops. This is actually real time. The red dot is the person's eye, zapping around, and well, it's quite difficult to see there. So I will go back to the beginning and say, here we are. The face at the center. The person looks at it. Oops.
They were trained before. Is the first time they did this exercise, or
Oh, you've been doing it all your life. This is what people do.
Yes.
Yes. With these images, never. I've never seen these images.
No, but I'm speaking the principle, because the face is not in a usual place, I would say.
Absolutely.
But
There
see,
is.
we find it quickly, I agree.
Yes.
But
So
can do-
this image, I think the beauty. I mean, we couldn't make a harder image, right? I mean, it's absolutely horrible. It's got so many things that could be a face. And where does the eye go? Where does the eye go? Where did it go? Where did it go? Where did it go?
So it somehow converged to the eye after some step, right?
You saw the speed. You're doing this 5 times a second. Now, this one I particularly love. Where's the face? It's actually up in the clouds up here. And this is, we deliberately replace the grayscale image by pixels for the face that have the same contrast. So there's no contrasting here. And you can see actually undershoot. You had to do a second saccade to get there. So we're doing 5 saccades a second, and the people do 500 of these in less than about 2 minutes. This should be an Olympic sport, right? I mean, this is, there are a few things that people can do 5 times a second. This is the only thing you can do. I mean, this is a real decision task. Build a machine to do it. You'd say, oh, they're difficult. Well, we did it in 2002, and it would do it for every. You would find all the faces in the image. Now, this turns out this paper came out a couple of months ago. There are neurons in a structure called the superior calyx of the monkey, which has direct connection from the retina, which respond selectively to faces in particular locations with latency around 50 milliseconds. It turns out actually they don't use the direct input from the retina. They have to go through the visual cortex where you have the orientation filters. The brain does this, but it's just extremely expensive because you need a neuron for every position and so on. We could do that on SpikeNet, no trouble at all. Did we make a fortune with it? Not really, but anyway, I mean, I'm just making the point that, these ideas really do work. It's just binary connections. And we're using intensity latency conversion, information contained in the order of firing, inhibitory circuits to pick off neurons the most active, N of M coding. That's you choose the N most active neurons out of M, where M can be any number you like. In the retina, there are 1 million fibers coming out. If you're lying on your back at night and you open your eyes and the first retinal ganglion cell to fire is in a particular location, that is the brightest star in the sky. And you've just picked the brightest. It took one spike to do that because you picked. Possibly, I'm simplifying a bit, but you get the idea. The more neurons you have to choose from, the more information you get from one spike. So one spike can transmit, in that case, 2 to the 20-bit. No, 1 million is forgotten. It's 20 bits or something in one spike. So it's incredibly powerful. And I think that could explain the remarkable energy efficiency of the brain. So if you compare conventional processing where everything's all floating point numbers for the activations and the weights, you can make that better with event-driven processing. This is sort of what there's quite a lot of things like dynamic vision sensors which send spikes, but they're still doing analog computing inside. You can make that better by using unary synapses like this. But you can do even better if you use unary synapses and N of M coding. And that's what I'm pushing. So all of these things on the left all require floating points. These don't. And in fact, the code that implements this, literally all you never add anything except 1. So it's, in terms of the software that it's just ink, you add 1 to the counter. And so the question is whether these ideas can be scaled up. And that's essentially the TerraBrain project, which I've been working on for some time. Aditya Kar was doing this and using just this Mac, for instance, which has 24 gigabytes of memory and a 2 terabyte disk and various things. This is actually Aditya's. I'm not going to show you the other thing actually running, but this is a video from this Mac, and it's I think it's 2 billion neurons, and each flip, it's about 8,000 neurons are firing. So we're getting a few frames a second. Now, that, I was already pretty happy with that. But then, well, first point to point, that simulation where each iteration, you pick off the n most active neurons, and then you propagate their spikes to the next one, and then you pick the next set of neurons. This will keep. I had this running through an entire poster session on my Mac with no power supply. It was on the battery because it's actually very cheap to do. But it's not doing anything because all these connections are random. But every neuron can connect to anybody else. There's
It's like a game of life.
it's yes, it will sort of I mean, it will happily keep going until you decide to stop it. Now, as I say, it doesn't do anything except it's alive. It's sort of propagating continuously. If you wanted to do something interesting, you'd have to train the weights using a learning algorithm, and we can talk about it in a moment. But stop press. And thank you, Milad. Where the first thing he did was we discovered how to get the lists of spikes read much more efficiently, because with an SSD you can in principle read 1 million things randomly from the memory every second. We were only getting 10, 15,000, something like this. And so now Milad's got an M3 Max chip with a Max chip. It's 16. It's got 128 gigabytes of unified memory and 8 terabytes of storage. And literally this morning, I just got this, which you can put 4 terabyte memory chips in, the sort of things you put in games machines and so on. Plug it into your Mac. You can daisy chain them. You can have 5, at least maybe 6 in a row. That will give you 80 terabytes going through one USB. This is a Thunderbolt thing. This thing is a mere Thunderbolt 3 thing, and that's the best I can do. But the new Macs announced in the last 2 days come with 3 Thunderbolt 5 interfaces, which each can do 120 gigabits of data. It's about 3 times faster than that. And I'm convinced that we will be able to simulate networks with more neurons in the human brain, more connections than there are in the human brain, and using software and hardware which you can buy at the Fnac. Now, this is the new mini Mac. It's this big, and it's got 64 gigabytes of unified memory. Got these 3 Thunderbolt 5 ports, each of which can connect to these memory things. So basically, you use your RAM to have your counters, and you use your external thing to have all your weights. And every time a neuron spikes, you read its connections of list, and you update all the neurons, and then you look to see who's got the most activity, and that's all it has to do.
So you updated neuron, and you compare it with the weights that you have on the disk.
The disk contains just lists. For every neuron in the system, you have the list of the neurons that it's connected to.
Okay.
So when it fires, you add 1 to all of them.
You look at what neuron does it find to
Connect to, which is completely the opposite of what everybody else does, I think, because everybody else says, I've got 10, I've got 16 billion neurons. Each one of these got 1,000 inputs. I'm going to recalculate for every neuron its activation level based on all of its inputs and all of those weights. That's the thing that makes it cost 20 megawatts, because it's stupid. The brain doesn't do that. The neurons that don't fire don't cost anything.
So those weights that you store on the disk, so it is loaded by the system, right?
Yes.
So then you fix those weights. So actually, the weight is a table of connections.
Yeah. I mean, I'm talking about Macs, but actually, I mean, a Snapdragon from Qualcomm is another chip which is also doing what do they say, 45 tera operations per second. I mean, so that this is this is hardware that you're going to get on everything, but it's not doing floating point mass, which is the important thing. So So just to summarize, a sort of a petabrain or terabrain architecture. And here I've got 2 to the 32 neurons. There are 4 billion of them. They can each connect to any one of the other ones, right? That system has actually 2 to the 64 potential synapses, but I don't care because I'm only interested in the ones that are actually connected. And so if you wanted to do what Jeff Hinton was saying, a memristor thing, you'd have 4 billion lines coming in here, 4 billion lines here, and you'd have 18 quintillion little devices that you're having to program. Sorry, Jeff, you can try it, but I don't think it's going to beat this. You wanted to ask a question?
Yes.
Yeah.
For each neuron, you have a list of neurons that is connected to the
Connected to, yes, it's the
connected
output.
to-
Yeah, so
So
neuron 1 is
first-
connected to neuron 11, 27, 4 million.
And this list vary and depends on neuron to neuron, or it has the same list for every neuron.
Oh, no, every neuron can have whatever, you can make any connectivity you like.
So, and these
No
neurons
restriction.
are the neurons that are mostly activated to that neuron.
If the system is switched off, it's just it's just that box full of 16 terabytes of numbers. If one neuron fires one spike, then you read its things in and so on. So amusingly, this is actually exactly what we did in 1998 when Arnaud Delorme wrote the first version of SpikeNet. We joked at the time that this system would simulate the entire human brain in real time, as long as no neurons fired any spikes. And that's essentially what we're doing now, except that now we can do 1 million spikes a second because the hardware works better. But it's the same idea. For every neuron that fires, you just add 1 to its target, and then you look to see whether those targets are interesting and gone over their threshold, or actually there are other tricks you can do to pick off the most interesting ones. So, I think in many cases, 256 connections per neuron is probably way more than we actually need. I think a lot of computation could be done with way fewer things, and that really makes the system incredibly efficient. Because if you've got 4 billion neurons and they've got 256 connections each, you need 4 terabytes. It's that much. It's a little thing this big. I mean, it really doesn't cost very much. So how does SpikeNet? How does this terabrain system compare with what everybody else is doing at the moment? Well, okay, Steve Ferber got massive amounts of money from the how am I doing for time? Okay, I'm nearly done. Billions of funding for the Human Brain Project. Then they built this system, Spinnaker neuromorphic supercomputer, and it reached 1 million cores. And it's switched on. Each core could do 1,000 neurons. So the total was 1 billion neurons. Have you seen the size of the thing? It was using 100 kilowatts of power. And the reason is, I mean, Steve's system was very good for sending spikes around, but the computations that were done locally were still horribly expensive, so it didn't really help. The latest version is now Spinnaker 2. So these chips. There's a company in Germany selling you things like this, and you can imagine the power consumption of that. It's not like a Mac. The world's first human brain scale computer goes live later this year. It may be on. It's called Deep South. It was built by in University of Western Sydney. It's basically it will do 228 trillion synaptic operations a second, and but it's using 40 kilowatts of power. And if you ask why is it still so astonishingly expensive, it's actually because the guys who did this, when they said, okay, we want to do all the neurons in the human neocortex, for instance, how many spikes will be generated a second? And they probably asked, a neurophysiologist, what's typical firing rates of neurons? And you often get people saying 1 or 2 spikes per second. And so if you say you've got, you know, billions of neurons and they're doing 1 or 2 spikes per second, that means, you know, tens of billions of spikes you have to do. And that's where you get the 228 trillion operations a second. However, I think that's all wrong because make this very, very quick because of time. It's quite possible that we've completely misunderstood what's happening in your brain at this very moment. When people record neurons, you only record from the neurons that have actually got any activity. You don't see the neurons which are quiet. So I've been pushing the idea, this is too, but basically right now, it is quite possible that many of the neurons in your head haven't fired a spike for months. You wouldn't know it. The neurons will fire when some old TV program that you haven't seen since you were a kid comes on. Oh, yeah, I remember, you know, Bewitched or, you know, whatever it was you were watching. You know, in my case, you know, 60 years ago.
Amusing.
Yes, so you got I got tons of neurons that learn old songs from the 1960s, which they can come back on. Oh yeah, I remember that one. Yeah, that was, and you activate all your memory. Those neurons don't fire most of the time, and that's why I think our brains are so incredibly power efficient, because I think people haven't realized that actually it has to be extremely quiet. It turns out that this was stuff that I worked on in I had an ERC advanced grant and made lots of provocative claims. I won't go through them all in detail, but basically, you know, the idea that the neurons, what I call near cortical dark matter, that the neurons are incredibly quiet. I mean, the jury is still out on that one. We don't know but we're going to know soon, because I was talking to some people recently who have been recording with optical methods the activity of the mouse visual cortex continuously for a month, and then slicing up the brain and seeing which of those neurons were firing, which of the elements are actual neurons, and so on. But anyway, to take home messages. So I think, you know, what I've tried to show you is that firstly, you know, there's the obvious case of how work on rapid visual processing, feed-forward processing, I think directly led to the 2012 deep learning revolution with Jeff Hinton and co, because it forced, well, it was Fei Li who came up with the ImageNet challenge, and that sort of basically gave a task which was comparable with what humans do all the time. But the second thing, which has not been exploited, is spikes, and the fact that we can use, if you're not Bill Daly at NVIDIA and you don't believe that you need 255 spikes to send an 8-bit number, then you can do a lot more efficiently. And the sort of things I've been talking about with NFM coding and unitary weights, allows you to develop these architectures which are extremely efficient and can learn, unlike, you don't need, you know, millions of training cycles. I mean, the thing will learn on the spot. Every time you show it something, it's learning. So that's my my bottom line. And I think that's the key to understanding the 20-watt power limit. And it drives me insane when I hear Microsoft and OpenAI going to spend $100 billion in building a 5 gigawatt center for doing AI, and Google wants to do the same sort of thing. I mean, the amount of money that's going to be thrown at these projects in the next coming years is just astronomical. I mean, there's so many problems on the planet you could fix if you had $100 billion. So one of the reasons why I'm here and preaching this is because I want people to understand that the brain actually doesn't do it the way many people think it does. It's much more efficient, and so AI still has a lot to learn. The brain. End of story. And do we start the wine immediately, or do we have some questions? Okay, a few questions. You don't get any wine until you've had some questions.
I ask the question?
Yes.
What are the learning mechanisms for these devices?
Okay, well, we
Is
have this.
there an equivalent of back propagation?
Absolutely not.
Absolutely not. So
I mean,
what are-
actually, you'd be very hard pressed to find anybody who actually believes that the brain does back propagation. I mean,
So
most people are agreed
can
that
we
it
do it in the
works.
lab?
It works. The proof is, you can build large language models and image recognition systems, and then it just need astronomical amounts of training. Now, the brain just picks up things. I mean, there's another story to tell about that, but we learn things on the fly. If just one illustration, we did an experiment where we were streaming ImageNet images. There are 1.3 million of them at rates up to 120 frames a second, and people were just watching these go by. And then after a time, you stop the thing. You show 4 images, 3 of which were shown once, and the other one was shown, let's say, 4 times, and people will pick out the one at 120 frames a second. I guarantee you don't see the images. The brain is just storing the stuff on the fly.
See, what was the success rate? I guess it was not 100%. Sometimes I may.
No. So you got 4 images
Yeah.
come up. 3 of them you've seen once.
Yeah.
One of them you've seen more than once, and you have to pick out the one
Yes.
which is. And people get 45% correct.
Yeah,
Chance is
which far
25.
more than expected.
Yeah,
if
I mean,
it's
you're not perfect, and in fact, people think they're guessing because they don't necessarily remember seeing. I don't know that one. Yeah,
So
and they
it
get
is
it right.
not back propagation,
No.
it's direct modification.
I would say
of
it's
the
that
of the solution.
our thing, which is what Bilal is doing with the image indexing thing that he's been doing for the last few months, is that you show an image and you store the weights instantaneously in one-shot learning, and you just learn everything. You just learn everything. It doesn't matter whether it's interesting or not. You have to learn it. In fact, we showed that if you're using auditory stimuli and you just have repeating pure noise, you learn that as well. I mean, you might think this is stupid. This is just meaningless. But actually, if it repeats, it becomes meaningful.
Is it possible to store all the knowledge, all the human being in a single terabrain or not? Is it enough?
Yeah.
And
He said.
Is it that functional? And
Well, I mean, our poor brain. We only have 16 billion neurons, and each of those in the cortex, and each of those neurons actually only gets to look at a few thousand inputs. So the things you can spot patterns in is actually very restricted. It's why it's very difficult to spot that a sound and an image are associated together. I mean, unless you're paying attention, you'll never notice that. Whereas you do notice things that go together locally. In a terabrain system, any neuron can learn about any other neuron, and therefore there are no restrictions on what it can learn. So if you were, I mean, particle physics or whatever, you've got data coming in, really complicated stuff, with events which are incredibly short and so on, and you're looking for some patterns which reoccur. Doesn't matter how many inputs you've got, actually, neurons would learn those. So, what applications of this? Well, how about searching for extraterrestrial intelligence? So you take the radio signals from some exoplanet and you look to see whether anything repeats. So you just keep storing stuff. And if the same signal appears 24 hours later because it's the 8 o'clock news on planet X, you would know it because it's storing everything. And the thing is, the number of things you could store is astronomical. And if I take 4 billion neurons and I say, how many different ways can I choose 10 from those? It's huge. I mean, it's more you'd need. There's more than number of atoms in the universe easily. But you can, but you only store the things that actually occur. That's the trick. So let's take text. There are 1.3 million characters in the what's it called? UTF-8 thing. It's the things you use on web pages to present every character that you can see on a web page in every language on the planet. There are 1.3 million of them. So you give strings of these things and you say which strings reoccur. Well, in French, it's words, right? If you were reading sort of Hindu or some other thing that you wouldn't be able to make sense of, there will be sequences which reoccur. You just learn those, and you've got a system that doesn't necessarily understand speech, but it will know. It will be able to say, "Oh, well, yeah, I've seen that before," and that's the first stage. And the second stage is to then link them together. So, if I want a large language model, if I give you the phrase. One small step for a man with a giant leap for mankind. That's because those three words make it extremely likely that the success, the things that come after will be that, and all of that sort of thing you can store. So all the things that large language models do by compressing everything into incredibly dense floating point number representations which nobody can understand, you would have a sequence of things where the word detectors are linked together and they generate logically what the most likely word is coming up next, or a choice of words, which is what large language models do. So I think you say, could all human knowledge be put in there? Well, you just take every book that's ever been written and you just neurons are cheap with this. So you could literally have a neuron for every word ever written. I mean, it's just Macs and SSDs.
Yeah, especially because there will not be used if it's not connected to the book. It does not occur, so it will not be a waste of.
You never. I mean, a neuron would be produce a detector for everything that occurs. But if that thing that never occurs again, well, you're not going to ever use it. But if it just so happens that every time the bell rings, the dog gets fed food, then before long it will start salivating when the bell rings. That's what learning is all about. We learn that there are things like that happen which are not dangerous, and therefore you can ignore them. But you have to process them anyway. And an example, I remember when I moved to Toulouse 30 years ago. And we live in Saint Félix-Lauragais, and we arrived in the summer, and we had the windows open. The church clock rang every hour during the night. Oh my God, we're never going to get to sleep. 3 days later, never did. Now, is that because my auditory system didn't hear it? No, it's because they formed neurons, and those neurons weren't connected to wake up, Simon, because there was nothing that happened. It was so you ignore the things which don't have consequences. But you have the system that will allow you to learn what to do if that happens. If the bell rings and it means we all have to evacuate the building because of the fire alarm, then you know what to do. But that's just storing lots of stuff.
Okay, well, that's it. That's one.
Then we
Actually, I have two questions, so I have one question. So, as far as I understand, is like for particular task, some specific neurons get fired in our brain.
Yeah.
But if you change the task, there might be different.
Oh yes,
sets of
there won't be
that-
one neuron fires.
So
You can actually choose how many neurons fire. The way to do that. So if I show you an image and I say, I've got 1,000 output neurons, and I say, give me the top 5, that is the ImageNet path, right? So you say report the 5 most active neurons on the output. But you can make it 10, and then you've got the 10 best, or you can pick the 1, and then it's the number 1 thing. So you can choose how many you get. So when you have a system where there's the image or whatever it is you're using as a cue is not perfectly matched to something, you will have a set of things, and that combination of things is what you can use to learn with. So yeah, the fact is that the probability of you getting exactly the same input the second time is actually not very high. But the important thing is that the neuron which was most activated is the best bet. That's all you need.
Thank you again, Simon.
Right. So thanks to Van and P. Marichal for joining in.